Okay, so announcement. So, the latest homework, like homework D2, the grader actually had a grade a little while ago. Then I looked at the grades and I want to make some adjustments. So made the adjustments and then had him go back and model changes on those adjustments. And so then he got those back to me. And so now I just need to review those, make sure everything looks good, and then I'll release those. So those are done. I'm just waiting to post them. I'm confident that he made the adjustments I wanted to make, but just want to double check before I post those grades. So that's what's going on with those grades. Those will be released ASAP. I just need to scan through and do a sampling and make sure everything's as I wanted them to be. Otherwise, looking forward, um, Lab 7 was extended a day due to that Canvas outage that was, I'm sure, a headache for everybody. It was a headache for me. I'm sure a lot of, it was pretty frustrating for you too. So hopefully everybody's able to get those in time. Otherwise, looking forward to Lab 8. This is the data collection lab. So that lab there. So this is meant to sort of be a practice for your input modeling report that you'll do with your team. So I give you a bunch of data, and then you use tools from this unit, Unit G, to fit models to them. So determining, is this discrete data? Is this continuous data? What sort of family does this make sense from? What would be the best parameters for this? Using tools from not only this unit, but tools that we're going to introduce, excuse me, inside Arena that will help you do the numerical fitting. So that's kind of the goal there. And it gives some guidelines on real world data collection as well. So again, it's useful prep for your final project. With that in mind, next week, we don't go to lab 9 immediately. Next week, we use that lab period or that lab effort for you to work with your teams on your input modeling report. So there are instructions online for the format of that report. It's a very short document that allows you to identify which system that you plan on modeling for your project and go out and do some very basic, not all of the input models you need, but gets a show that you have access to the system to get sort of a little bit of data. Like here's we went for an hour and we got some arrivals to this system, and so here's our arrival data, and we fit a model to it. It looked like it was Weibel with these parameters, and here's why. Just sort of to show me that you have some momentum, so that we can let you go after this to continue forward. Because the last thing I want you to do is not have any real world data before that last week of class and then try to scramble. And it's one thing to cram building a model overnight, but actually gathering data is something that you really need to do ahead of time. So this input modeling report is just supposed to encourage you to actually get hands on your system so that you can get some of that data in. So in order to give you time for that, there won't be a formal lab. The lab next week will be used instead for this collection with your team for the input modeling report. Then after that, we've got labs 9 and 10. These introduce more advanced concepts in Arena. And then after that, there's still going to be weeks left in the semester, but we won't have formal labs. So those open labs will be to provide you time so that you can work on your final project. So that's the schedule of labs moving forward. Any questions? I've already started to get some of your project, your groups submitted, and have started creating those groups. So that's kind of sort of an important next thing here is to get your names of team members in. So thanks to those who've already done that. If you haven't done that yet, then there is a spreadsheet in the final project group module inside Canvas. So Canvas modules, final project group, that allows you to list your name if you're looking for a group, or your group if you're looking for a member. Go back to it after you've edited it to see if you can find a match. And then if you found a match, it's great if you can remove your names from that. So if worst comes to worst, at the end of this whole process, if there's a couple of stragglers, then I'm going to have to manually add them into existing groups or create a group of stragglers. And so it's good to sort of try to be proactive and pull those groups together yourself. That makes for the most productive teaming. So that's what's due here Friday to Canvas. So definitely take a look at that. So again, any questions about what's required immediately and in the later term for the project? Okay. So otherwise, ICAs continue to be available. I mentioned that the last homework, the grades are there. I just need to post them once I'm comfortable with them. And then there's another homework here, homework H. So this is a statistics application to input modeling and output validation. So you're going to do another chi-squared test, a more generalized chi-squared test, and then you're going to do a power analysis. And so those will be the two big sections of that homework. And then there's a homework J2 after that. That's the last homework of the class. That's a homework that can't be dropped and you won't get a solution to. That will feel more like a lab. It's more of a synthetic assignment that we use to capture some ABET data on the course, some accreditation data on the course. We have to do it in all of our courses. And so that was one of the big assignments tapped for this course to speak to those metrics. And so that's why it's treated a little more, it's special and it's a little more integrated than the rest of the homeworks. Okay, and then of course, just keep thinking about your final projects. All right, that's all the announcements and admin. Everybody good? All right, I didn't really get many who showed up at the office hours. Then I realized halfway through that if Canvas was down, which it actually came up during the office hours, it may not remember the Zoom room, but so I assume that there weren't a lot of questions about the final exam, but if there are, again, feel free to send me a note or come to office hours or make an appointment and we can talk about any of those final exam questions. Or if you want to kick any final project ideas, want to see how well they work or whatever, you want some input before you submit your input modeling report, then also feel free to reach out. Okay, so moving forward then, we're in this input modeling unit. So, input modeling, as a reminder, if you think about Lab 6, we gave you a really simple system in Lab 6, but then we asked you to change the arrival rates and the service times in this really simple system. And what hopefully you saw out of it is when you changed those things, you got significant changes in the outputs that were coming out of that system. So even though the system had not changed, it was this really simple, basically queuing node, by changing those models, so by switching it from a so-called MM1, where this would be exponential and exponential, to like a DM1, where these are deterministic and this is exponential, and so on, by switching these things around, then you get very different performance results out of your system. So your system is not just the diagram of where things are going. Your system is also the inputs, the probability distributions going into those diagrams. So the examples here is if we give you a queuing model, inter-arrival times and service times, those are definitely the inputs that you're going to need to gather data on. We give you supply chain model, demand and lead time. We give you reliability, failure time. So if you have mixtures of those things in your problem, you'll definitely need to be looking for data on those things. Okay, so distributions of these, those come from the real world. Poor choices of those, that will be the thing that causes distance, daylight between your model and the real world. Okay. And those in the back, it's just, I think the sound is carrying. If you're, and it may not be distracting to anybody else, but it's like going straight into my ears, like both conversations that are going on. And so it's just like, for some reason, it's really distracting today. So I apologize, didn't mean to call you out, but just, it's helpful. So, okay. As we mentioned before, like what we're sort of starting into here is that the easy part was hypothesis testing. If you've got a hypothesis, I think my data came from this, here are actual data, then as you'll experiment with in the next homework, we have statistical tools like the chi-squared test, which are relatively easy to apply and be able to say that, yeah, I think this is a good fit or not for these data. But the harder part is coming up with that hypothesis to begin with. And that's really what we've been sort of starting on here. So we did the data collection last time, and then today we're talking about how do we actually find that hypothesis to begin with that's up there. So that's what we're going on to here. So data collection was last time, identifying that probability distribution, that's this time, and then fitting it and evaluating the fit, that's next time. So let's, to motivate that, let's look at this simulation study again from the metal detector. We talked about this last time a bit. Let's make this a little more exotic, gesundheit, and show how the data can actually help drive us to different choices about which inputs to use. So so if I want to create this module, I would create this model. I can create an entity, people, with these pictures. I can create a resource, metal detector, with a fixed capacity. I can then, on my flow chart, bring in a create module so that these people arrive, create a process module so the metal detector gets seized, delayed, and released, and then a dispose module to collect them all. So relatively simple process, looks like this one. So you've now had some experience building these things in various labs. So last time we talked about, well, what if the summary statistics, the mean and standard deviation are both equal to 30 seconds? You just assume that's an exponential. Then you look at an exponential and you say, if it was an exponential, that doesn't make a lot of sense because the time it takes to cross through a metal detector is very rarely going to be close to 3 minutes. But there will be output realizations that are close to 3 minutes just for someone walking through a metal detector. So that's your metal detector passage time distribution. It just doesn't really make sense if it's just an exponential. So you take a histogram and you find out that it's bimodal. So it's got this large peak here and this short peak over here. And this large peak is maybe kind of what you expected. Maybe this short peak is not quite what you expected. And then you realize that the way they took the data, then those who got flagged for scanning, for rescanning, were that total time. So it wasn't just the time that took to go through the metal detector. The person who did the timing, when they started the stopwatch when they were at the front of the metal detector, and then they ended the stopwatch when they walked out of the system. And so what you're seeing here is a group of people who walked straight through the metal detector, didn't get flagged, and then walked straight through, and another group who then got flagged for extra screening and then walked through. And so you're actually seeing two populations here. So so this is what the histogram would look like if I did the CDF. So we're going to learn to talk about this today a bit. If you, instead of plotting the histogram, where I hope you saw in some of the previous homeworks, the choices of your bin sizes really changes how much shape you can see in the histogram. So histograms are really tricky. They're not easy to apply well at first unless you have lots and lots and lots of data. But you don't have to do any binning by plotting the so-called sample CDF. So where you sort the data on the x-axis and you plot it against its rank on the y-axis. And so you get everything from rank 0 to rank 100%. And that's what gives you this sort of rising curve. So that's your sample CDF. And when you see a flat spot in the middle of your CDF, that corresponds to an empty spot in your PDF or in your histogram. So that tells you this is a bimodal distribution. There are two areas that have two rising areas separated by a flat area. So it's a bimodal distribution. So there's probably two populations here. So I'm going to split that data up. And now I've got two input models. So by looking at something that I thought was one input model, seeing it was multimodal, and then saying, okay, I don't have a good multimodal distribution. There's a couple, like there's something called a beta distribution that you can get multiple modes out of, which doesn't really apply here. I haven't talked to you about a beta distribution. And all the distributions I've talked to you about, none of the easy distributions, the Lego bricks that you have available to you to build input models, none of them are multimodal. So I think, well, maybe rather than coming up with a purely empirical distribution, what if I split these up and I treat them as two separate populations and then model them separately? Then I start seeing some tractability. This over here looks like maybe it's an exponential. In fact, the mean and standard deviation are close together, like we would expect with an exponential. And this over here is kind of hump-shaped. Maybe it's a normal distribution. And if I think about it, if these were people who were going through extra screening, it makes sense that they would be a normal distribution because they go through different sequences. They say, all right, stop here, assume a certain position, wait for a second while I wand you. Maybe they get a pat down, maybe they get questions, all of these things added together. Well, whenever things get added together where the length of every individual thing is independent of the length of all the other things, that tends to make things bell-shaped. or bell curve shape. So that tends to make things more normal. So it kind of makes sense that this single wait time of walking through the metal detector is exponential, and this might be kind of normal. So I split those up. Well, that also makes me wonder, how often do people get put into one population or the other? So that introduces a third input model, which is a simple probability. So what's the probability that you're going to get flagged for extra screening or go through? So by looking at the data, by seeing that as a multimodal distribution, it telegraphs for me that I need 3 input models for the one that I originally assumed, and I need to restructure my model. So that's what we're going to do here. We're going to say we've got a long passage time distribution, a short passage time distribution, and a probability. So 3 distinct input models that I'll build into here. So how do I do that? I go in, I drag decide module in, that's for my probability. I get another process block for the additional input model, and maybe another dispose block so that I can dispose the ones who went straight through the metal detector separately from the ones who went through extra screening. So if I grab all of those, I get a model that looks like this. Everybody arrives at the same spot. A fraction of them get checked and go through the delayed entrance. And if the other half or the other portion go straight through the metal detector and go through the quick entrance. So this is a total revision of the structure of my model just by looking at the distribution of the data. So that tells me, how many input models I look at. Sometimes your data will speak to you and will tell you how many models to choose. So from there, then, I can now study the impact of this detection probability. So a lot of times when people want to speed things up through these security lines, then one of the strategies is to educate people coming through the security lines so that they're ready for them. So if you could say, well, how much effort do we need to put into educating people so they know to take their belts off, they know to empty their pockets, all of these things that make for a smooth security experience, how much effort should we put into that? And by going into my sim and changing the probability of triggering the detector, then I can see the output of my sim varies from here where it's mostly exponential, and the mean for the whole population, this so-called mixture model, where it's a mix of 2 different models, the mean of this model is only 10 seconds. Whereas over here, where there's a population that's very new to this process, and so everybody gets flagged and everybody has to go through secondary screening, then the mean here is a minute. So just by changing this probability, I go from this shape to this shape to this shape, and the mean of my whole distribution goes up. So that gives me a parameter that I can experiment with, and then I can report back to the people running this system to say, if you can just do this, this is an opportunity for you to improve the performance of your system. So that's like for my experiment. Now, how do I actually fit this probability? Well, to the real data to figure out where we are. Well, I mean, something I can do is when I look, if I go back to this split that I originally did here. Oh, sorry, I went too far. This split here, if I look up, oh, sorry, that was right. If I look here, I can see that there's 588 people in this group who are less than 40 seconds. And those that are greater than 40 seconds, there's 412. So right there, I see that there's a 58.8% chance that you won't get screened. Or I guess I should have said a 41.2% chance that you'll get selected for extra screening. So from my data, I can actually get that probability as well. So if I split these populations, I can use the fractions of the total populations to get the probability. And then I can go into my modified model and experiment with that probability to see how much of an improvement I can make by, say, putting up more signage or paying people to stand there as people come into the building and remind people that, take off your belts and so on and so forth. That's why they pay people hourly wages, in order to just bark at people to, instructions for security lines, because it actually ends up saving them money in terms of throughput, even though they have to invest in the person giving those instructions. So that's an example where we used the data to guide our input modeling choices. And so I want to take that to a bigger, another extreme here. What if we saw this histogram instead, which corresponds to this CDF? So notice here, I've got multiple flat spots. So there's multiple rising spots that are separated by those flat spots that correspond to these multiple peaks. So now I have a multimodal distribution. It has this comb of different locations where where outcomes are clustered. What might this be? How could I explain this? What is a hypothesis for the structure of the system that could generate data that looks like this for this security system? What are your thoughts? Why might you get these multiple peaks? So I've got, this peak here. In fact, if I go forward, so here's my first peak, and then here are all the rest of the peaks. And so we could say these are people that went straight through a metal detector. But why would people who got selected for additional screening maybe have this distribution of their times? What sort of structure of the system might we guess would produce that? It's just a guess, just a hypothesis. So there could be lots of answers. What do you think? Anybody? So multiple humps where, some people, it takes them, let's say 60 seconds, around 60 seconds. The next people take around 120 seconds. The next take around 180 seconds. The next take around 240 seconds. And there's less and less and less as you go down. But it seems like each group of people is separated by about 60 seconds. But there's less people as you go on. So more people get through the system in 60 seconds. And then there are a little less people take 120 seconds, a little less people take 180 seconds, and so on. So what might generate this population distribution? I mean, have you gone through security systems and have you got selected for extra screening? What often happens after you go through and they say, oh, you left your belt on, take your belt off. What often do you then, after you've taken your belt off, do they just let you through, or what then maybe happens? Yeah, you go back in line. Right. You might be prioritized, you might be in the line, but you go back in the line. And that means you go back in the line for the metal detector, right? And so then you've taken the belt off, but you might have forgotten that you've got custom orthotics in your shoes that have metal in them. So what happens? You get flagged again. So they say, oh, shoot, I forgot. I've got these shoes. I'm going to take my shoes off. I'm going to put them in the bin. And then they'll say, all right, sir, go back around to the metal detector, go through again and again and again. And so what we might be seeing here is that these are people that get flagged once, have to go back through the metal detector. But then these are people that get flagged twice. So they went through the metal detector, got flagged again. And that might be what we're seeing here. So if we see that, then we say, okay, so we need to adjust our system here. So if that really is the way we're doing it, then what we would expect is if we look at each peak individually, so these are the people from 45 seconds to 85 seconds, and these are the people from 150 seconds to 200 seconds. And we can see that there's fewer people here. So the histogram is a little uglier, it's a little sparser, but it's very similar in, like, the standard deviation of these two things is very similar. So it is conceivable on face value that this is actually the same distribution as this, but this one's just fewer people. So what we might be seeing are copies of the same secondary checking distribution shifted by the 60 seconds it takes to ask somebody to get back in line and to come back through screening again. So if that's the case, then maybe we can build that into our model. And so here is our adjusted model that accounts for that possibility. So we've got our arrivals, just as before. You walk through the metal detector. You go through this detection probability. Some just go straight through. Some get checked. And then they go back through and redo the whole process again. Some of those will end up going through detection and get out of the system, but there's going to be some unlucky people that get checked, flagged again, and then it'll go back through. And that will keep going over and over again until hopefully everybody gets out. There won't be anybody who's in here more than 4 or 5 runs because that'd be extremely low probability. But maybe this better explains our data. So we put that in as our hypothesis, and then we go and we see whether the output matches. Since that would be the kind of next step there. So that would be the output validation step. But so we allowed the input to structure our model to give us a hypothetical model. So then we see, do we get the peaks through here? And I do know that this system can generate that data because that's how I got the data. I built this system first, and then I generated that data. But hypothetically speaking, I could have gotten that data first and then used that to inspire building this system. And then the next step would be then to get data out of this and then use something like a chi-squared test, or there's a number of different tests we could use that could then validate, or a chi-squared test would be fine, or a KS test maybe, but a chi-squared test probably, to say, let's look at the data coming out of this system compared to the data, the output data coming out of the real system. And if these data look like our total output data, then we've got good confidence that we've figured out the mechanism there. So we use the histograms to inspire the structure. We run data through the structure and then check whether the histograms we get out of the structure match the original histograms that inspired the structure. And if they don't, we calibrate, and so on and so forth. And so we'll talk more about that as we get further on in the class. But just, the big thing here is that, it's really important to look at the shape of your distributions. If they're nice, single mode, unimodal distributions, then you can often go straight to the input models. But if they've got a lot of weird structure to them, you've probably compacted multiple processes into one, and you probably need to rethink, do I need to break those things up and make my model more complex to make my input models less complex? Okay, so any questions about that? Let's see how we went from looking at the data to adjusting the model structure to account for weird things in the data. Okay. All right, so once you've identified an input model, we need to figure out, or once you've had data, you need to figure out which family. Like I mentioned that this one group looks like it's probably exponential. This other group looks probably like it's in the normal family. Well, how do I really evaluate those choices of families before I then go and fine tune my choices for those particular data? And that's what we talk about today. And so we've already talked about the histogram, so we're going to sort of drill down into that, and we're going to land in PP plots and QQ plots and then next time, then we'll be talking about choosing the parameters. So this is what we're focusing on today. So histograms. Now I hope you've seen already, I've asked you to generate histograms in some of your homeworks. And so I had you generate a random variate distribution where there was where it had a very strong peak just to the left of the axis. And if your histograms were too chunky, then that it might have looked like a uniform distribution all the way across, because that really strong cluster of numbers right next to the axis would have gotten grouped together with additional bins. And if your bins were too large, you may not even noticed that there was a slightly, there's an excess set of numbers close to the axis. So that's an example where if you choose too chunky histograms, then everything looks uniform. But if you choose too fine histograms, you don't see any shape at all because you only get one thing in every bin. And at that point, it just looks like a bunch of dots on the axis. So it's difficult to figure out, how to do this. And so there are alternatives to the histogram, like these kernel density estimation that in more advanced classes you'll start doing, where they're much smoother approximations of histograms. But histograms are still, a workhorse of statistics. So still a lot of people use them. So how do you choose your class intervals? So for continuous data, the good rule to start with is the number of equally spaced bins is the square root of the sample size. So if there's 100 samples, choose 10 bins. So you just take the square root of how many samples, and that's how many bins you equally distribute across the observable range. But if it's for discrete data, you bin every output separately. You don't want to bin groups. If it's discrete data, you don't want to group things together in some sort of a hyper class, a super class that has multiple, because you really do want to represent every single outcome. So that's a key difference between these two. So here's some examples. So like, this is the same data that has been binned 3 different ways. So I would say that, this one has probably been binned into 2 mini bins. So the max number of counts per bin is 6, but most bins are like 1 or 2. So I don't really get a sense of the shape. I get an idea that there is a lot of data around here, but I don't really see how the distribution falls off. Now you could go the other route and you could create these really giant bins like this one here. And then I get these 3 bins, and it's clear that there's something happening in the middle, but I lose sort of information about the tails. So there's a bunch of different distributions that would look like this. It could be triangular, it could be normal. I can't really tell. So I'd say that's too chunky, too few bins. Whereas this one, I start getting the idea of like, oh, I see some fine-grained shape without degenerating into just looking at all the individual data. This it sometimes is a little bit of an art, but when I ask you to generate a histogram, I'm not, at this point, I know that all of you can generate a histogram. So this isn't like the class where we learn how to do histograms. This is the class where we learn how to use histograms. And so when I ask you to generate a histogram, don't just generate the first histogram Excel gives you, because Excel does a really bad job at this. It's your job to say, like, now as you're moving into becoming data experts, it's your job to choose the bin size that you feel best represents the data. And so you have to use your quantitative background to say, I get more useful information out of this third one down here. Does everybody see why this third one's a better choice? So even if Excel gives you this, don't try. They're software engineers. They don't know anything about data whatsoever. So don't trust the choices that somebody at Microsoft made in that histogram tool. You guys are the data experts. Right-click on that data, say go to whatever format data series, and then choose your own bins so that you get closer to something that looks like this. Okay, but for discrete data, it's a little bit different. So here's discrete data. So we've got arrivals per period. So these are counts of arrivals. And so we're saying that like we counted arrivals in 10-minute periods. And so every 10-minute period got a different count. So in this 10 minutes, we got no arrivals. In this 10 minutes, we got 18 arrivals, and so on. So we can then take all those counts, which are discrete, and then we get a frequency distribution here. So there were 12 10-minute intervals that had 0 arrivals. There were 3 10-minute intervals that had 9 arrivals, and so on. When you have discrete data, you don't want to blur outcomes together. So your histogram should have 1 bin per outcome. So a bin for 0, a bin for 1, and so on. And that's what you've got right here. And so you get this histogram here. And hopefully you'll be getting to a point when you look at a histogram like this, you'll say, hey, your brain is going to go to, oh, that looks like a Poisson. And it should partly go there because you know that if it's a count distribution, it's probably in the kind of binomial series or it's in the exponential series. And on the exponential side of things, the Poisson is the way in which we model counts. And so there's not that many options for you to sort of think about without any other data. And so I look at this and I say, it's kind of like you got a big cluster around 0, a hump in the middle, and then a big tail that goes off that way. That kind of looks like a Poisson. So that's just intuition you build up. But the big thing I'm going to take away here is if it's discrete data, don't cluster things together. Every outcome gets its own bin. All right, so everybody clear on that, what I mean by that? So continuous data, choose your bin sizes to make the shape clear. Discrete data, you don't have a choice. Just bin every outcome. Okay. So once, when you're choosing these distributions, if possible, it's nice to choose distributions that your simulation tool automatically has built in and implemented for us. So in Arena, if you go to any one of these fields where you can put an expression in and you right-click, you can go down to Build Expression, and it'll bring up the expression builder. And under the expression builder, under expression type, it has a whole group of random distributions. And so these are the distributions that are immediately available for you to implement in Arena. And so, and it's pretty much, most of the ones that I want you to know for this class, plus maybe a couple of others. So it's the common vocabulary of these distributions. And so it's nice. You click on them, and then over here, it shows you the parameters for it. So for a triangular, it has the minimum, the most likely, and the maximum built in there. You fill those things in, and then down here, it auto-populates the expression for that. So it's nice if when you're choosing a distribution, if you don't really have a reason to choose one over another, if you can find a distribution in this table that seems to be a good fit for your data, then that's going to help you down the line. Now, if all of these are terrible fits for your data, don't shoehorn one of them, shoehorn your data into one of them. But if they seem like one of them seems like a reasonable guess for what your data looks like, then these are good places to start. So that's what I mean by choosing a family of distributions. Okay, so how do we choose that family? So I've given hints of this already. Context. Oh, this is a count variable. This is a time variable. So it can be, it's got to be non-negative, and so on and so forth. Do you know physical properties of that variable? What do you know about that variable and the causal factors that are driving it? So is it discrete or continuous? That's the first thing you should ask yourself. Like, is it possible for this thing to take values in an interval, that it's continuous, or are all the values come from a set of like 5 options, then it's discrete? So that's like the key thing, because those distributions are way different from each other. And then after that, is it bounded? Does it go to infinity? Does it stop? It can be continuous, but bounded. Other features, is it memoryless? So do I have an insight that if you know how long you've waited, does it not give you any information about how much longer you have to wait? So that would indicate that it's memoryless. And if it's a continuous distribution that's memoryless, it's got to be exponential. So knowing things like that help drive you to these things. I mentioned before additive. So is it the result of a bunch of steps being added on top of each other that are independent from each other? Then maybe a normal distribution is a good place to start, and so on. So you look at those things, and that kind of gives you an idea of where it might be. And then you look at the shape of the histogram or the shape of the CDF. And then from that, then you can sort of say, well, based on the 6 that I thought it might be, this is, these 2 are the only that could generate this shape. So it's okay if after you make your choice, there's some features that just aren't accounted for. Stochastic modeling is about fitting the major trends in the data. It's not about fitting every aspect of the data, especially rare parts of the data that are unlikely to typically drive system performance. So we were trying to search for a good approximation, not a perfect fit. Often the good approximation is better because it'll generalize. You might have gotten pilot data that had some weird thing because on one of the 30 days that you were taking data, there was an event that happened, a terrible storm or something like that, and it caused some of your data to be abnormal. And so if you're designing your system, you don't want those abnormal days to drive too many of those decisions. So oftentimes, choosing a model that's actually a slightly worse fit makes it more generalizable to the implementation, which may not have that weird anomaly that happened when you were running your study. So it doesn't have to be perfect. And I mentioned, exponential, normal, Poisson, uniform, beta, triangular, gamma, Weibull. These are ones that are frequently encountered. So those are ones that you should always have in your back pocket ready to try. But, there are other things that are out there. So don't feel like these are the only things you can use. There's bias if you always go to these ones. But know that these are, the reason they're so well known is they're used a lot. So these are ones that are useful to know. I haven't taught you anything about the beta, but looking forward, if you do a lot of this, if you need a bounded continuous distribution that has some funky shape, then the beta distribution is a great go-to for that. So, but that's not something you don't have to worry with the beta in this class, but just know that as you do this for real, then these are the ones that come up a lot. All right. Questions about any of that? Or we drill down into that. So we're now going to see, how we pick these families and then how we evaluate the fits without choosing parameters. Okay. So, as I said, is it discrete or continuous? The key question you should ask yourself. This is what we mean by discrete. So the histogram has got a bunch of gaps in between it. So if you make these bins smaller and smaller and smaller, it doesn't change the distribution here because they keep collapsing onto a single point. So if you have data that look like they could be discrete, make sure that your histogram bins are small enough that you have accounted for every outcome. Or even better, just use if you're using R or or Python or other statistical programs, you should be able to ask it, how many unique values do I have in this? And it will then report out that, oh, there's only 7 values in these data. And you say 7, I see 4 peaks here. And then you can look at those 7 and you realize that 3 of them were grouped together in this peak or something like that. But if it comes back and says there are only 4 values and there are these 4 values, then it's a discrete and you only have 4 outcomes. Notice that the outcomes aren't integers. They don't have to be. It's not about what number the outcome are, it's how many outcomes there are. And so there are 4 outcomes, that what makes it discrete. It might be it's 2, pi, 5.5, and 6.75, whatever, some other number. They don't have to be equally spaced to be discrete. They just have to be a countable number. Versus continuous, where as you take the histogram, there's no daylight between observations until you get bins that are so small that there's 1 per bin, and it's just like because you didn't sample enough of them. But once you start making the bins slightly larger and you get rid of all of the gaps so that everything's smooth, then it's a continuous. So that's a key way to tell discrete versus continuous. Gaps or no gaps in the PDF. In the CDF, it's steps versus smooth rises. So if you do the sample CDF, which again, that's when you take all your data, you sort it lowest to highest, and then from your data, plot the sorted data on the x-axis against its rank in the ranking on the y-axis, divided by the total number of data points. So this is saying that 2 is the very lowest. So it's at 0% in the ranking. There's 0% of points are less than 2. Whereas 7, or it jumps up to 7 here, or actually, I guess it jumps up at 6.75. It's saying 100% of the data are less than 6.75. That's how we read this. And when we look at that, where we plot all of the data against their rank, then we see these steps. So what we're saying is there's a bunch of repeated outcomes here, and then there's another bunch of repeated outcomes. Sorry, I should say these are the outcomes that are repeated. So there's a bunch of repeated outcomes, this vertical step, and then no outcomes, and then repeated outcomes, and then no outcomes, repeated outcomes, and no outcomes, and then repeated outcomes. All of the vertical rises are the outcomes. So if you get practice, if you look at this, you can see the histogram. You can see the probability mass function, and it's the height of those steps. They just happen to be stacked on top of each other. Over here, for continuous data, if I do that same exercise, I get no vertical steps, so no repeats. And so instead, I get this nice smooth rise. And so that's what a continuous CDF looks like. Any questions about those distinctions? Discrete CDF versus continuous CDF. Or what we mean by sample CDF, sorting your data and plotting by its rank. Okay. And then, so these are the ones that I'm hoping that for this class. So, we've already talked about these, so I'm not going to spend a lot of time on them, but I did include in this slide deck for those that are going back to the slide deck, whatever, just a refresher from previous lectures that were brought in these slides. But these, again, are the building blocks of most of the input models that you'll do at this stage. So if you can't fit one of these, there is a data-driven last resort that I've written down here in Arena, and other sim tools have it too, where you can create an empirical distribution. And what that basically means is you take that empirical CDF and you encode it as its own distribution. So the disk function, which we talked about before the midterm in ARENA, you can put that CDF. So you can have the cumulative probability of an outcome paired with its outcome, and you can pair that against all of the outcomes. Remember, these are cumulative, so this one should always be 1.0 over here. And then that's if you just didn't have a discrete distribution that had parameters here. You can just basically put your data in, and it will generate new data that matches the proportions in your existing data. So if your existing data had a certain probability mass function, it will then draw from that probability mass function. That's what this disk does. This is a last resort. These are much more generalizable. These allow you to average out the weird anomalies that happen during data collection and generalize to the rest of the cases that will occur later where those anomalies were not going to show up. But if none of these are working well, then this is an option. Likewise, if you can't find a good continuous distribution, then there is a slight modification of disk called cont, or continuous. And it takes the exact same inputs as disk does, but it connects them so that instead of having so it basically puts a little uniform distribution in between every outcome. So whereas in the disk is going to say, you've only had 6 outcomes, well, then I'm only going to generate 6 possibilities. In the cont, it starts with the probability mass function for the disk, but then it puts next to every peak, it puts a flat line so that you get these little micro uniform distributions so that it now represents all the numbers in between the outcomes as well. So this is, again, if as a last resort, if nothing's working up here, then you can create a data-driven distribution to draw from. But it's highly recommended, especially for continuous, to pick a continuous distribution. Okay. So questions about any of that? About what I mean by empirical distributions down here, data-driven distributions? All right, and like I said, after this, I'm going to skip through these, but for those that want the refresher in this slide deck, I've mentioned, I've got the slides reminding us what the normal distribution is for, and I've got down here, a reminder of its interesting features and how, tips from your system can help tip you off that you should use a normal. I've got that for the exponential as well. I've got that for the Weibull and Poisson. So those are all there. So now speaking of the Poisson, so we mentioned this is from before, this Poisson distribution that was up there before. Poisson takes this one parameter alpha. So sometimes when you need an exponential arrival in your model, you want to go out and take data on inter-arrival times, continuous data, but that's really tedious to do. So imagine going to Sky Harbor and you would like to try to figure out a good arrival rate for everyone arriving to Sky Harbor. Sky Harbor is a very busy airport. So if you were trying to get the inter-arrival times between everyone showing up at Sky Harbor, it would be, there'd be a lot of those, and it would be very difficult to get those with any high resolution. But remember, the Poisson is related to the exponential in that the Poisson is a count of exponentially spaced arrivals. So that means that when you're taking data, even if you need an exponential inter-arrival, you can take data on a count of arrivals and then turn that into an exponential. And so that can be very valuable for your input modeling. It can save you a lot of time. And so what do I mean by that? So what I've got behind me are a count of arrivals in a 10-minute interval. So this is saying here that there are some 10-minute intervals that have 50 arrivals. In fact, most of them, I would say a lot of them, have got 50 arrivals. There are very few, but some 10-minute intervals that have 70 arrivals. And there are a few, but some 10-minute intervals that have 30 arrivals. So there's a whole distribution of these. So you can imagine you go to Sky Harbor, and instead of counting inter-arrival times, instead of being there with a stopwatch, you have someone say, count off every 10 minutes. And so, so they'll say, all right, I started my next 10 minutes, start counting. And then you just start counting. Okay, every time somebody goes through the door, you count up and you get up to 30. And they say, oh, 10 minutes are over. Okay, then you reset your counter. And you do that over and over again. And you get these data instead. Now, I don't know the interarrival spacings at this point. I just know these. But I can fit a Poisson. And that Poisson tells me that I get on average roughly 50 arrivals every 10 minutes. That's what I get from these data right here. Now, what's cool about that is if I take that 50 arrivals and I divide it by the length of the time interval, so 49.9 or 50 divided by 600, so I want this in per second, so 600, that's 10 minutes in seconds, then I get an arrival rate of 0.08 arrivals per second. And that I can use as a parameter for an exponential. And if I then use that, then so basically this histogram here, these are data that I basically used this exponential to generate arrivals that were spaced with the exponential. Then I counted them up, and that's where I got the previous histogram. And then I used that to fit an exponential to the data that I generated, and I recover the exponential out. So that's this dashed line that's going down here. So even though I did not take inter-arrival data, I would just took count data, but I can then turn that count data into exponential data by dividing by the interval and using that as my exponential rate. Now that only works because I was confident that in this interval, they were exponentially distributed. So I can do this, like there's that homogeneous arrival rate assumption. So if I was looking at data over the whole day at Sky Harbor, I know that people don't arrive at the same rate all day. But I can say, in the hour of 9 to 10, I could probably approximate that as one rate. In the hour of 10 to 11, one rate. So I can generate one of these Poissons for every hour, and then I can figure out the rate per hour. I could not do this for the whole day. Once I do that for the whole day, I probably will get something that doesn't look Poisson. But if I even try to fit a Poisson to it, then the exponential rate that I get out of it would be nonsense. All right, so that simplifies fitting your exponentials. You don't have to measure every inter-arrival time. You can just count how many arrivals happen in an interval. Does that make sense? So there are questions about that. It's the fundamental link between Poisson counts and exponential spacing. Okay. And then again, this is just a cheat sheet, but what I've added to this, you've seen this before the midterm, but I've added to each one of these is the ARENA expression you use to implement these. So if you want to draw something according to these things, then here's how you do that in ARENA. So again, these are just up here, not for me to go over in class, but for you to have there as a reference for how to get to these things easily in ARENA. Okay. And only thing I'll mention here is as you start fitting data, like you're going to start doing in Lab 8, ARENA will try to fit the most flexible distribution to your data because it will have the best fit. And that will very often be a gamma distribution, which is basically an Erlang distribution where k is allowed to be any number, not just integers. And that is going to be a better fit because it is more flexible. But it isn't necessarily, if you can get an exponential to work and it's almost the same fit, fewer parameters is better than a good fit. So that you have to penalize your choices by the number of parameters. So the gamma distribution has got 2 parameters and exponential's got 1 parameter. If this shape parameter in your gamma distribution is really, really close to 1, it's really, really close to an exponential. So when you're doing these fits, you'll get a more generalizable fit if you've got less parameters and a similar fit quality or R-squared value as it'll be portrayed or in ARENA. So that's just another thing there. So when you're doing your input modeling reports and then in your final projects, when you're showing me your input models that you chose, if you choose things like the gamma distribution or the Weibull, you have to justify to me why you've chosen an exponential modifier instead of an exponential. So if there are these things that are really meant to be there to sort of bend a distribution like an exponential to the will of your data, and your data actually looks pretty exponential by itself, you have to justify to me, why did you choose a 2-parameter distribution when a 1-parameter distribution would have been just as fine? So be careful, because ARENA is just going to fit. It's going to give you the best model, the numerically best model. And so it will choose the most flexible model. But you can force ARENA to say, actually use an exponential instead. I don't want you to fit a gamma. So be very careful when ARENA starts spitting out gammas and Weibulls at everything, because they're so flexible. We don't often want the flexibility if we don't need it. Questions about that? Okay. So be prepared to justify your choices. All right, so let's then the core of this lecture then are these PP and QQ plots. So I want to make sure that we spend the last bit of time here on that. Okay, so we want to figure out, we have a couple of families to look at. We don't want to bother with fitting every family numerically, figure out its parameters. So how do we then say this family is likely better than this family without actually figuring out the best parameters for each? So we're going to use these things called probability plots, which if you've seen in other classes, maybe you've heard people refer to fat pencil tests. This is the same sort of concept here. So we focus here on two things, the QQ plot and the PP plot, and these both are based on the idea of the sample CDF. And so we're going to, in these cases, sort our data like we would for evaluating a sample CDF. But now that you've been able to plot those sample CDFs by sorting the data and plotting them against their rank, then these QQ plots and PP plots take that to the next level, where they say, okay, now that you've plotted your data, let's plot what a hypothetical distribution might look like on the same plot and see how well they line up without actually doing the numerical fits. And so I'm going to show you how to do that. And there are two ways to do that. And we do the QQ plot first, and if it turns out that it matches well, then we move on, and any further discrimination we want to do between distributions, we do with a PP plot. We don't do the PP plot first. But you have to kind of meet the conditions of the QQ plot before the PP plot works well. So, so let's see how each one of those works. So let's start with the QQ plot. So the core is down here in both of these things. I've added some extra detail here, but how does the QQ plot works? So we're going to sort our data. We do that with both the PP and the QQ plots. Sort your data, but then you plot in the QQ plot, you plot your data against, not against its rank, but basically against the rank that it should be if it followed the hypothetical distribution. And what do I mean by that? You plot it against the inverse CDF of its rank, where you do this little rank correction where you subtract off a half from its rank to kind of center it, and then you divide it by the total number of data. That gives you kind of a corrected rank, and then you run that corrected rank, which will be a number between 0 and 1, into the inverse CDF of the hypothetical family that you're going, and this could be any member of the family. So you just say, you know, if it's a normal distribution, just pick the standard normal. The parameters here won't matter in the choices here for this hypothetical distribution. This is the idea that we're trying to fix the family, not the parameters. And then we're going to evaluate how well this looks and look for a linear relationship. So what does that look like? So here's an example where I generated some data. And so the data that I generated were a normal distribution with a mean of 5 and a variance of 9. But I used, for my hypothetical CDF, a standard normal. And so I plotted all the data that I got out on the x-axis, and then I took its rank, its normalized rank. So I took its position minus a half, divided by the total number of data. That gave me a number between 0 and 1. And I took that, I plotted into the inverse CDF, which we all know about now because we did all that stuff with inverse CDFs before the midterm. So I put it into the inverse CDF for a standard normal, And then I get these data out that fall pretty much on a line. That means that these are close to a normal distribution, that maybe a normal is a good choice for this family, or that a normal family is a good choice for these data. So alternatively, if I would have drawn exponential data, but I want to compare to this hypothetical normal, so I do the same thing. So these are exponential data. They come from an exponential distribution with a mean of 5, but I'm trying to test the normal family. So I took all my data, I plot my data on the x-axis, I take its rank in the ordering, I run that into the inverse CDF for the hypothetical standard normal here, and then I get data which are not very linear. They're bowed like this. And so the best line I get is here, and there's a lot of daylight between that blue curve and that dashed line. So that tells me that this is probably not a good family to choose. And so, in fact, I can use deviations from linearity to guide my next family choice. And so there are these rules, and I'm not going to go through all of them, but this is an example of them. They're in the slides. But the basic idea is there are these patterns, like the left end is above or below the line, and the right end is the opposite. Well, under those cases, it tells me that, let's say here, if I've got the left end below the line while the right end is above the line, that tells me that there are longer tails than my hypothetical distribution on both ends of the data. So my hypothetical distribution falls off, but my real data goes for, it's more represented in the tails, in the edges. So that tells me that I probably need to choose a new family that's fatter, that is more represented on the edges than in the middle. So I can do the same game here. So this, that goes the other direction there. Down here, if it's got a curved pattern with slope that's increasing from left to right, data is relatively skewed to the left. It's more extreme values on the left versus the curved pattern with slope decreasing from left to right. So if I go back to this one here, notice that the slope is high and then it rounds off. So it's a curved pattern that gets shallower as it goes on. Well, that's exactly this case here. Curved pattern with slope decreasing from left to right. Data is relatively skewed to the right, more extreme values on the right. Well, yeah, the data I drew is from an exponential. So it's got a huge amount of skew. It's got, everything's pulled to, I guess for you, it'd be pulled to the right. So there's more values over here. So that tells me that I chose a normal distribution that has no skew. It's symmetric. And this is saying, no, you really need skew. You need a lot more skew than you've got, and it should be skewed to the right. So I can read that right off my QQ plot. So you look at your QQ plot, and and if there's deviations, it guides you to hopefully a better one, so that you can go from something that looks like this to something that looks like this. And that tells you in the ballpark. But there might still be multiple families that look like this. So that's what we use the PP plot for. All right, so but before I move on to the PP plot, which is a slight deviation, questions about this? Okay. So we do that, and we find that there's two that look like a line on the QQ plot. So then we go to the PP plot. PP plot starts out the same way, sort your data, but we're gonna now plot kind of the opposite thing that we plotted before. So now we're gonna plot on our x-axis the rank. So we're gonna plot here, we take our, the rank minus 0.5 divided by n. So this is our sort of normalized rank with that little correction by 0.5. And then we take that and we plot it against the rank that we would expect for that value under the hypothetical family. So we take the data that we got out and we plug that into our hypothetical family, and then that will give us a value between 0 and 1. And so then we've got our x-axes are between 0 and 1, and our y-axes are between 0 and 1. And if those fall on a line, in fact, fall on the diagonal, then we've got a good fit. So let's see what that looks like. So here I generated data from a gamma distribution with these two parameters. So remember, this is basically an Erlang 5 distribution with this rate, and then 5 is our shape parameter. And so that's what the real data are. Now, if I look at these, so that's what the blue histogram is here. Here's a gamma distribution. This red histogram, this red solid histogram, but the green dashed histogram, that's a normal distribution with mean 50 and variance 15.8. And it also looks like my histogram. So I can't really tell which one's which. So I end up doing a QQ plot and they land on top of each other. The QQ plot can't tell the two of them apart. So then I go to my PP plot, and in the PP plot here, I've got, again, this empirical, so I've got this normalized rank on the x-axis, and I've got my hypothetical rank, what I would expect if those data points were run through the CDF for both of my hypothetical distributions. So I got my hypothetical gamma with its parameters, my hypothetical normal with its parameters, and I see that this red line, which corresponds to the gamma, falls right on the diagonal, but this green line has some daylight. So that gives me ideas that, okay, so it's probably the gamma, which I knew because I generated the data. But if I didn't generate the data, I wouldn't know that. And this PP plot would help give me more guidance that I should go towards the gamma over the normal. That's my PP plot. So questions about that? You do the QQ plot first. If you get a couple things that fit, then you do the PP plot to split them up. Okay. So takeaway messages here. Look for lines in the QQ plot. They used to call these fat pencil tests. So the idea is that if you took a fat pencil, like a carpenter's pencil, that was sort of, it's kind of long, you could lay it down on paper, it wouldn't roll away. If you take that fat pencil and you were to lay it across your data, you should cover up all your data. That would be a good fit. So both in the QQ plot and the PP plot, if you put a fat pencil down, you wouldn't see any of the lines peeking out from behind the pencil. That's the so-called fat pencil test. So you look for lines or fat pencils in the QQ plots. If you have large deviations, you use that to help you pick a better distribution. Once you've figured out the better distributions, and now if you've got a couple that look really good in the QQ plot, then you can use your PP plot to discriminate among the distributions with those that basically fit in the tails. Basically what's happening is the QQ plot fits the tails, the PP plot fits the middle. So you've pinned down the tails of the QQ plot, and then you compare the middles with the PP plot. And then these PP plots typically are uninformative if you do them first. So you typically want to do them after the QQ plots. So if you've got, so this would be wonderful in your input modeling report if you had a QQ plot and a PP plot. If you said, I took these data and I chose this distribution, and look, I did a QQ plot and a PP plot, and the distribution I chose, my data falls right on top of them in a line. That's a great way to validate that you chose a good family of those distributions. And then you fine tune the parameter choices in tools that we were going to talk about in the next lecture. But that's, that would be good evidence. And it's great you see that in papers, and whenever you want to try to justify you've picked the right distribution, you should see these plots as some evidence that your distribution makes sense. Okay, because if you can have bad fitting families that you still fit, you can choose the best of a bad family. So the methods that we learn next lecture, you can apply to bad families too, and you'll find the best of that bad family, but you need to show me that it's a good family, and that's what these graphical methods do. Okay, so like I said, that's what we're going to start on next time. Any questions? Not, then let's do the clicker. Question is, what comes first, a QQ plot or a PP plot? And you can just put two letters, QQ, or one letter. You could just do Q or P. Oh, sorry, my bad. All right, that's just to see who's paying attention. All right, so PP or QQ, what comes first in the analysis? A PP plot or a QQ plot? And that's all I've got for you. So we'll see you Thursday.